So how does 5G mobile NOMA, the non-orthogonal multiple access scheme, compare to the previous schemes of fourth generation and third generation mobile comms of the OFDM and the CDMA? Okay, well, if you want to know more information about NOMA, there's a video on the channel, and NOMA uses successive interference cancellation. So let me draw the rate region for successive interference cancellation. And again, as I say, there's more information about this on another video in the link below. So here's our rate region, the rate that can be achieved by user 1 on this direction, the rate can be achieved by user 2 in this direction, and I've drawn it for a scenario where user 2 has being received with higher power. So potentially user 2 is closer to the base station than user 1. And so here's our rate region here for the successive interference cancellation. This is in NOMA. Okay, so let's think about how it compares to these previous schemes. Well, if you have a time-sharing scheme like TDMA or an orthogonal frequency subchannel sharing scheme, then these schemes on this rate curve live on this line here. So this is the line for TDMA and also for FDMA, or the OFDMA. Multiple access. So this is TDMA and FDMA. And on this line here, what you have is that if you're going to only in an orthogonal way, let's take TDMA for example, for a portion of the time you're going to send with user 1, but not any of user 2, and then the other portion of the time you'll let user 2 send, but not user 1, then you're going to get a fraction of user 1's rate, and when you're sending to user 2, you'll get a fraction of user 2's rate, and it's going to live on this line. Of course, this is the maximum rate you could get from user 1. This is the maximum rate you could get from user 2 if it was the only one sending for all the time. And so this line gives the trade-off. It's important to make a point about this line. This trade-off is the trade-off when you are transmitting at a given power level. So when you're turning on user 1, it transmits at a power level, particular power level. And so this line here is assuming that you're not changing that power level based on the fraction of time that you are transmitting for. So you're just keeping the same power level. So what it means is if you're turning on for less time, then sending with that power, you will, in that less time, you'll have used less energy. So that's the trade-off that occurs and is assumed along this line, is that when you use less time, you're actually using less energy, but you're allowing the other user some time to use its power and therefore get some energy. That's what it gives on this line. There are different curves for TDMA and FDMA under different power assumptions. But this is one here. Okay, so where does, and it's the same for FDMA, of course. So where does CDMA lie on this curve? Well, it depends on the flavor of CDMA. So let's think for a moment of purely orthogonal code division multiple access. So you're using an orthogonal code to divide up the two users. Well, in this case, there's two users, so you need a code which is of length 2 to make them orthogonal. And if you do it in the standard CDMA orthogonal way, then you'll do 2 code chips for every symbol time period, which means you're using double the bandwidth. Okay, so on this curve here, because this is bits per second per hertz, therefore if you're able to get this rate for this amount of bandwidth, then if you're going to do an orthogonal code, you'll be able to get this, you'll be able to get the same amount of data through, but it will require twice the bandwidth. Therefore, this number here gets halved on this diagram. But you are sending both of them at the same time in CDMA. So in CDMA, purely orthogonal CDMA achieves this point here on this diagram. So this is because this is half the maximum of rate 1 and half the maximum of rate 2. And that is because this is in bits per second per hertz. And that's because to achieve that orthogonality, you needed to use twice the bandwidth. So this is orthogonal CDMA. Okay, now it's not always the case that it's possible to get orthogonal CDMA. That requires a lot of coordination of all the codes amongst all the cell towers and all the users, for example. So typically there is interference between the users. They're not typically fully orthogonal. So another way of interpreting CDMA in terms of code division is not to use orthogonal codes, but another approach is you could use Gaussian codes. And if you use Gaussian codes, then in fact, it makes it more difficult in terms of code distribution, even more difficult in terms of code distribution, because Gaussian codes have much more randomness in them. But from an information theory point of view, that's actually the optimal thing to do. So you can get a better rate combination if you use these Gaussian codes. And where do you achieve? It turns out you achieve this point here. So why is it that you achieve this point here? So this is CDMA. This is CDMA with Gaussian codes. So SSIN codes. Now this is the actual information theory best that you can achieve with CDMA. So what you're doing, instead of thinking of them as spreading codes, which make the two users orthogonal, in this case, you're thinking of them as error correction codes. And so what you're doing is both users are transmitting at the same time. The other user is being treated as noise, and you are doing coding on your user to correct errors that arise from all of that noise. That's the way to think about it. And so why is that? Well, here, exactly with the same logic and thinking about in terms of successive interference cancellation, but you're not doing successive interference cancellation when you're doing this straight CDMA. What you are doing is each user is decoding their signal under the assumption that the other user is noise, or treating the other user's signal as noise. So this number here is, of course, log 2, 1 plus power to user 2 divided by the power to user 1 plus the noise. That's the, again, if you want more information on this, check out the successive interference cancellation video on the channel. And this number down here, of course, is the same, but for the user 1. So it's 1 plus power 1 divided by P2 plus N0. And if you decode both of the users, not using successive interference cancellation, but you just decode both of the users under the assumption that all of the remainder of the signal is noise, then you would achieve this rate pair here. So this is CDMA with fully orthogonal codes. This is CDMA where you are doing the coding for error correction, and you can see that the sum rate is higher for this because the distance along here plus the distance there, the sum rate, the sum of the two rates, is bigger than this distance plus this distance. And just one final thing with CDMA is in cellular deployments, it's often the case that, of course, you need to think about the interference to the neighboring cell. So it's often the case that in these situations where one user is stronger than the other, you will tell that user that's stronger, in fact, to reduce its power. So this is power balancing, power control, so that in fact you can increase user 1. So here, for example, user 1's only getting this amount, is getting even less in this case, although the sum rate is more because user 2 is getting more. But if you reduce the rate from the power to user 2, it means you're going to reduce its rate and you're going to operate at a point here on the 45-degree line where you're getting equal rate for the two users. Okay, so this point here is CDMA with equal rates. And so certainly user 1 has a bigger rate than it got in either of the other two versions of CDMA, but it came at the expense of user 2 having a significantly lower rate. But this is often important for cellular networks, and this is the price that you pay so that you don't get interference into neighboring cells, and also that you increase so that the two users are getting an equal amount of rate, which is in some cases the fairness that you're looking for. Okay, so hopefully this gives an insight into the capacity region and also highlights how good the successive interference cancellation is, because it's far on the outer region. These rate points that you can achieve with successive interference cancellation are far better than for CDMA, TDMA, and FDMA, which is the reason it's been selected for 5G mobile. So if this video has been useful, give it a thumbs up. It helps others to find it. Subscribe to the channel for more videos, and check out the web link in the details below this video where you'll find a full categorized list of all the videos on the channel.